All right.
Good afternoon.
Is it time?
I think so. It's 3:31.
Okay. Good afternoon, everybody. My name's Ricardo Garcia. I'm a product manager here at Emerson. I deal with the PRV group, and my product line is the PRV monitoring product line, which is not really a PRV per se, or a type of PRV. It's an accessory, right? One that we're seeing more and more traction. And so today we'll cover why it's important to start monitoring PRVs, some of the technologies that we use to monitor PRVs, and also the regulations that are requiring us to do PRV monitoring in the field. So first of all, we'll start with some introduction really of PRVs in general. So PRVs are the last line of defense that we have in our plants against overpressure protection. So think of a good example is a pressure cooker in your house, right? That pressure cooker has to have some sort of way that if something happens inside and the pressure continues to build up, that it won't get to a point where it explodes, it damages your kitchen, it could damage you or whoever's around the pressure cooker when it explodes. And so, again, they're critical to protect not only against overpressure events, but also against underpressure events. And so that's why we have some types of PRVs that are meant for vacuum. There's combination style PRVs that are pressure vacuum relief that will either let some process out when we have overpressure and let some air in when we have under pressure, so that we don't implode the tank. And because we're dealing with assets that protect personnel and protect equipment, they're heavily regulated. Here in North America, there's regulations from ASME, there's regulations from API. The national board is who ensures that those regulations and standards are being abided to. And it's standards and regulations that apply to how we test a valve, how we manufacture a valve, how much a valve flows. And all of this regulations obviously are very important in PRVs. And here we have some examples of what happens when we don't pay attention to the way that we size our valves. They can lead obviously to catastrophic explosions, damaging personnel, damaging equipment. Basic operation of PRVs. This is the most common type of PRV. This is what's called a direct spring operated valve. And it's basically think of it of a counterbalance of forces. You have one force acting up, that's your system pressure. You have one force acting down. Typically, in a direct spring operated valve, the name gives it away, that's a spring, right? So the spring, again, is providing a force downwards trying to close the valve. The system pressure is providing force upwards trying to open the valve. When you reach an equilibrium, that valve will start to lift. Okay? Because they're safety devices, they have to be mechanically and self-operated. That means we don't rely on external air. We don't rely on electricity. They're control valves, we operate those with, you could operate them with air, you could have an electric actuator on them. That's not the case with relief valves. Relief valves have to be able to operate by themselves. And because they're, again, mechanical devices and self-operated, they're typically what we call off-grid. That means we don't really have visibility into what a PRV is doing in the field. Typically, that has been the case for a good number of decades. And finally, the importance. So these valves are found everywhere in plants. Everywhere that you have a pressurized vessel, you have to have a way of having overpressure protection. And because they're, again, critical for safety, you cannot bypass these valves. So what that means is that if your valve is down for whatever reason, your process cannot operate if you don't have overpressure protection. And a way we say that we like to think of pressure relief valves is they're a compromise. You're compromising emissions and product losses. In exchange, you get your personnel safety. So it's a compromise between emissions, product losses, and safe. So historically, because we don't have any visibility into pressure relief valves, historically, the norm has been that we do preventative maintenance schedules on PRVs. That can be dictated by local regulation or by your plant's internal regulation and standards. So those can be, you have to inspect and retest the PRV every 6 months, every year, every 2 months. Every 2 years. And so another thing is that PRVs are difficult, very, very difficult to access. They're meant to be on top of these vessels, and they can be several feet up in the air. They can all be set, for example, we're leading into a common header. And so if you have a pressure relief event, sometimes you're required to figure out where that pressure relief event is coming from. And again, you have to send people with sniffers and testers to go around doing manual rounds, exposing your personnel to unsafe environments. It's expensive to get people up there. And also when they need to be removed and reinstalled, you're talking about 4 man-hours when the valve is easily accessible. It's about 6 hours if you need scaffolding, 6 to 8 man-hours if you need scaffolding. It's about 8 to 10 hours if you need a crane. I've seen it before to where they have to take roofs off of buildings to get these into these PRVs. And so what I'm trying to say is every time we're removing PRVs, you're not only losing process uptime, but you're also investing a lot of money into getting to these PRVs and being able to work on. So the idea is if we can reduce the duration and the frequency of how often we are servicing our PRVs, then that will save us cost and also improve our personnel safety. So we at Emerson did a study of service records from a large oil refinery in the Gulf region. This service record spans over 7 years. It's 10,000 service records, and this is Emerson valve, and this is Ferris valve, this is consolidated, so it applies to all valve manufacturers, the big ones. And what we've determined, so the first thing we do when we get a valve that is being sent to us for testing is we receive that valve and we do what's called a pretest. A pretest is without us touching the valve, without us doing anything to the valve, looking at the internals or anything like that, we just expose the valve to a set pressure that is what it's supposed to open. So if the valve is set to open at 200 PSI, we receive it, we expose it to 200 PSI and see how that valve is behaving. And what we determined from, again, 10,000 service records, 7 years of service records, is that 20% of those valves that we received, so we're talking 2,000 PRVs, were leaking below 50% of set pressure. So that means, again, let's go back to the example of a 200 PSI set valve. When we get to 100 PSI, there's noticeable leakage at the outlet of the valve. And 8% of them were leaking so excessively that our test stand did not have enough volume to reach a full lift capacity. So that's obviously a safety problem. And there's no way, because we work off of preventive maintenance cycles, there really is no way for us to determine when that valve started to. And we have determined that a valve that's leaking 0.1% of its capacity over the course of a year that it goes undetected is the same as having the valve fully open for 6 hours. It may not seem like much, but if you have 20% of your entire fleet in your plant that's leaking just 0.1% of its capacity over the course of a year, that's a lot of product loss. Moreover, when we do this, because we don't know when that valve started leaking, there really is no way for us to do a root cause failure analysis of why that valve started leaking, because we don't know. We don't know when it started, right? If you're lucky, you might have, when you're inspecting the valve, you might see something like this. This is what happens. So these are the seating surfaces on a metal seated valve. And you can see that some type of debris got caught between the seating surfaces when the valve slammed shut. damaging the seating surface, and from that point on, that valve is going to continue to. If you have a way of knowing when your PRV went off, and you see that it started to leak after it went off, you could go back and see and correlate that with things that were happening in your plant to figure out if you can determine a root cause failure that that you can go back and then modify to prevent this from happening in the future. So when we have undetected pressure relief events, we have analyzed this and talked to the end users, and we've categorized the problems that happen from undetected pressure relief events into 4 main buckets. The first one, of course, is emissions. We know we're all here for a reason. The emissions is honestly what's being the biggest driver for PRV monitoring in the most recent years, but it's really not the only one. Again, when the PRVs are opening or when they're leaking, we're putting dangerous gases out into the atmosphere. Production is another one. Again, just like we were saying, a 0.1% of capacity equals 6 hours of lost product. But in reality, most valves, when they're leaking, they're not leaking 0.1% of its capacity. They're leaking more than that. And so that's an easy quantification of really how much energy and how much product is being lost due to just PRV leakage. Then the other one's reliability. Reliability goes more with how available our process is. Because again, if a PRV has been compromised and it's out of service, then your entire process is down. You cannot operate without a PRV unless you have an immediate backup for it, which more often than not is not the case. And then finally, safety. In fact, we've had, unfortunately, there was an incident in the Middle East. It was a valve that was in H2S service. The valve was relieving and it was leaking through a flange, and there was no way of knowing which one exactly it was. They sent somebody in there, and unfortunately, they had a fatal accident there. And now they're doing monitoring on all their valves because they want to know exactly when it releases and which one it is. So Mo's going to talk more about the regulation.
Thanks, Ricardo.
Mhm.
So I'm going to talk a bit more about the current regulation that EPA has out in terms of PRV monitoring, like PRVs in general out there. So in 2019, EPA had a regulation for the refinery sector where the refineries had to monitor all pressure relief devices venting to the atmosphere and hazardous air pollutant service. Now, this time around, what the EPA has done is they've come out with a similar regulation, but a lot more stringent for the chemical industry, and they call it miscellaneous organic chemicals regulation. I think it's 40 CRF 63 subpart FFF. Now, this in general does mention chemical industries, but if you look at the scope, it's a lot larger than just chemical. So they're covering essentially all the other industries other than refining with a lot more stringent regulation than the refining industry saw. The rule goes into effect this year, August 12th, where it says all pressure relief devices that went to the atmosphere in hazardous air pollution service need to be monitored. So we're and the regulation mentions it as PRDs, pressure relief devices, right? So PRVs do fall under that, and surprisingly, more often than not, you would find a decent amount of PRVs at facilities that are venting the atmosphere. So all of them would need to have some kind of monitoring technology to be able to understand when these valves do go off. So a little bit from like an excerpt from the regulation itself. They say that they're explicitly mentioned a monitoring system, which was not as evidently mentioned in the refinery sector, the regulation when that came out. So this is again, it's a little bit more stringent, and they're given a decent number of examples of what kind of technologies would be used, right? So you have the first one I hear, which is essentially like a rupture disk, but when they mention rupture disk, it's you got to either monitor the rupture disk or the valve, right? But we'll see in a little bit, it kind of helps monitoring the valve more than the rupture disk because we need to have quantifiable measures. So in that aspect, it helps if you're able to monitor the valve. A magnetic sensor on a pressure relief valve stem, that's something like a position monitor that Ricardo will go into in a little bit. A flow monitor or pressure monitor is something like, well, somehow you're able to calculate flow through the valve, or you're able to get better indication of a quantitative measure of what happens every release event, that does occur during, that for a relief valve that meets the specific criteria, right? And Ricardo will go into that a little bit more as well. But essentially, the biggest issue that the industry is seeing right now is being able to quantify the quantity of organic hazardous pollutants for each and every release event, right? Because if you there's a fine line between actual reporting, over reporting, and trying to get a better understanding of what's the accurate amount. Because if you continuously just assume 100% open, depending on how many times the relief happens, and you're reporting that continuously, sure the EPA is not going to be too keen about it, right? So over time, you could be looking at severe fines, you could be looking at inspections. So it's just trying to have better visibility into your process and optimizing it on your end before anybody else comes and starts snooping around, essentially, right? So in terms of reporting, every release event that occurs, you would need to give the start date, start time, duration in minutes, right? So you need to know when it started and when it ended. You would need to have a mass quantity of flow. So you would need to have how much quantity flowed through that valve. And for every release that occurs, you need to do a root cause analysis. So what changed in your process to cause that relief valve to go off? And a corrective action analysis, say, what are you going to do moving forward to help mitigate this release from actually happening? Now, this is for every pressure relief valve in the facility that's rented to the atmosphere in hazardous air pollution service. So if they do go off, it's a lot of work. And then you don't want them to pretty much go off. But when they do go off, you want to know completely when it does, how long, and how much actually went out there. So you have accurate information in terms of reporting. So in our solutions, and Ricardo will talk a bit more about that too, is we see it as a twofold solution to tackle the regulation, right? So the first one is to ensure you have the correct type of valve in terms of your sizing, in terms of the application. Your valve is such that where it automatically has minimal releases based on the valve design. And the second one is to have accurate monitoring technology to help you get insight into all the required variables that are needed to be reported. Any questions? Do you want to dive into it?
Sure. All right, thanks, Mo. So after understanding a little more about the regulation and what it entails, we'll now cover the solutions that are out there for monitoring PRVs. And we think of this as somewhat of a tiered solution. The first one is the 708, which I'll talk more about in a minute. And then it goes up from there as to what more information you get. And we consider that we have basically a solution for every application. Because there's some applications that all you want to know is when the PRV relieves. It's in a small valve. It's in a small valve that's already relieving into a common header. So this first one is what's called wireless acoustic transit. This technology is wireless only. It uses a mesh network of wireless hard infrastructure to bring the information back to your control system. There's a software that does all the quantification and reporting for you as well. And this basically works. There's two sensors in one, basically. There's an acoustic sensor, and right now we're not really talking about audible acoustic. Acoustic is more of the way that waves propagate through matter. And so this, if you want to think about it, it relates more to vibration than it does to audible acoustic energy. And so this device is straps on the outlet of any PRV. It's non-intrusive, and it's also what we call valve agnostic, right? Because it can go on our valve, it can go on anybody's valve. And again, two sensors in one. So it's measuring, again, the acoustic vibration, and it's also measuring the skin pipe temperature of the outlet. And why do we measure the temperature? Because, so if you take a look at this graph here, the blue are those acoustic counts that are common. This is a unitless measure, we just call it counts. But it's again, that vibration, or that acoustic vibration. And then that green is the skin pipe temperature. And so we have an increase on the acoustic signal signifying that something's happening, and then it's paired up with a rate of change of temperature. Now, this rate of change can be positive or negative, depending on what is your process. Is your process hot? You might see an increase in temperature. Is your process cold? You might see a decrease. So we're not really looking for a threshold of temperature. We're looking at rate of change. Are we seeing both conditions met? Do we have an increase in acoustic counts and also a rate of change of temperature? And that would signify that you have a pressure relief event. This again is wireless only, so it uses an intrinsically safe power module to power the device. And depending on how often you're sampling, you set the sample rate when you program these. You can set it to sample every second, you're going to be changing batteries. We say that if you're sampling every second, which gives you the best resolution out there, it's about a year for the battery. Now, if you go to the 4 to 6 second range, you might change batteries every 3 years. And we think that that's the sweet spot, if you ask me. If you go to 16 seconds or 30 seconds, you might be changing batteries every 10 years, but you might lose some of that resolution because you're only, it's like opening a door every 16 seconds and you don't really, like 20 people might have gone by, but you're only opening it once every 30 seconds, you might lose some people that went by, right? So that's acoustic transmitters. Any questions on acoustic transmitters? Right?
What kind of range do they have?
The range as far as distance?
Yeah,
So again, this uses a wireless mesh network, and so you have to have several points for the distance to bounce off, the signal to bounce off. But this particular antenna, and I don't know why they express that in meters, but it's about 150 meters, and there's no obstructions. If there are obstructions, it gets derated by a little. Yeah. But they do have an option for an extended range antenna. It can be all the way up to a kilometer if you have the extended range antenna.
it's not even a kilometer.
There you go. Well, there you go. Okay, this is solution number 2. So one thing that I didn't mention here. So yes, it is a transmitter, which is giving you a range of information, but there really is no way to correlate acoustic counts to how much the valve is open. And so for reporting, if you want to do reporting of what's happening in your pressure relief event, you have to assume, hey, this is giving me start time, this is giving me end time, I can calculate my duration, and I have to assume that the valve is full open for 100% of the time of the pressure relief. Now, that is not always the case. That's not really how relief valves operate out in the field. What we've learned through years and years of studying relief valves and testing them is that first they go into this process called simmering, which is when the disc is just slightly off from the seating surface, and you're having some pass through it, but you're not really fully relieving yet. Then it goes into what's called substantial lift. And there you go at to or pretty close to 100% open. And then it finds an equilibrium point that's somewhere around 85 to 90% open. And it hovers there until the pressure relief event has been taken care of. And now we close back down sort of gradually. And so this pressure relief, our monitoring device actually tracks the lift of the valve through time. So this is what's called a position monitor. It uses a Hall effect sensor, so we have to add a magnetic target to the spindle of the valve. It's kind of like the stem of the valve, if you want to think of control valve nomenclature. You add a magnetic target, and that magnetic target writes up and down in a channel on the position transmitter, and that's what gives us our position. Obviously, the bigger the valve, the larger the travel. You have to use different magnets, but always the same device can cover all sizes. And the added benefit that you get from this is, again, you get a lift percent capacity or a lift percent travel in your valve, and that gives you more accurate volumetric information of what was happening during the pressure relief. Any questions on this? Okay. And finally, the Cadillac of solutions pertains more than anything to pilot operated valves. So a pilot operated valve, just to summarize real quick, is a type of valve that consists of two components, two main components. This blue component here is what's called the main valve. This is what holds the system pressure. This is where the seating surfaces are. And this silver component here, that's the pilot. And the pilot valve is what holds the setting of the valve. It's like the brains of the operation. This is, in fact, when we're setting these, we don't even set anything in the main valve. We only set the pressure on the pilot valve on the test end, and then we test it all together afterwards. But when we're setting the valve, we're just looking at that pilot valve. And then there's obvious advantages here. And the big advantage, you would think that pilot valves are always more expensive than direct spring valves. And that's true for the low sizes. But as you get into the bigger size valves, if you need a spring in a valve that's 4 or 5, I think 4 inches is where they kind of overlap. 4 or 6 or 8 inches, that spring becomes huge, and you're talking a lot of material that you're saving by not having that spring there. And so in the larger sizes, pilot valves are actually more cost effective than direct spring valves. But the way this works, and I wish I had I don't think we do. The way this works is in the main valve, there's the area underneath the seat, and we take pressure from that area. You see that tubing coming off of here, and that pressure goes into this pilot. The pilot then allows that same pressure to go into the secondary chamber at the top of the main valve, and that's called the dome. The dome has a 30% larger area than the area underneath the seat. And so when the valve's closed, the same pressure that's in the inlet is also in the top of the valve in the dome. Same pressure. And so if we add a pressure transmitter there and the differential pressure transmitter tells me that the pressure is 0, the differential is 0, then we know the valve's closed. So when this valve is approaching set pressure, what happens is that the pilot, there's a spool inside the pilot, and the spool moves, and there's a feedback piston in here too, and those move to let air or pressure escape the dome. So we're reducing the pressure at the top of the valve, and the pressure at the bottom of the valve staying constant. We're starting to move from that seat, and that the internals in the pilot valve will modulate depending on what's needed by the pressure relief event. And so our main valve is also modulated. So the good thing about that is you're only relieving as much as needed by the pressure relief event. Whereas direct spring valves will go into an insignificant lift when we hit that set point. A pilot valve will modulate. And so again, we have story or history from users and our own testing, and we've determined that a modulating pilot valve on average will relieve about 50 to 60% of its capacity, as opposed to close to 90 from direct spring valve. So again, going back to what Mo was saying, the best solution for compliance will not only have the best monitoring type, but will also have the best valve selection for less releases. And so again, because we're monitoring that differential pressure, there's a direct correlation between that differential, or a mathematical equation that converts that differential pressure to valve lift percent, and we can track that over time. And in here in this graph, we're just showing the closing of the valve, but again, it's more gradual. So to summarize the different technologies, I've taken, for example, a 3x4 valve in natural gas service set at 50 psi, and that valve has a capacity of about, let's call it 5,000 SCFM. And we're going to assume a minute release because that's convenient. And so for option 1, we have a direct spring valve that's being monitored with an acoustic transmitter or a limit switch. A limit switch is just a discrete on-off type of thing.
It could be like the wired solution to the wireless acoustic.
Exactly. And so in here, again, the information that we get from our monitoring is we have start time, we have end time, we calculate what that time is, and we say, you know, in actuality, because we know that that valve was not really fully open that entire time, in actuality, that valve relieved about 4,000 SCFM, but our report is gonna say, no, we relieved about 5,000. So you're over-reporting in this scenario, and you're also over-emitting when you compare to a pilot. In the second scenario, we're using a position transmitter, so we're tracking that position across time, and the valve or the transmitter is now telling us the real story, right? Again, significant lift, then we find equilibrium, and then we close back down semi-gradually. And so for this scenario, the actual release is about that 4,000 SEF that we were talking about, and your report is going to match that. So you're still over emitting as opposed to a modulating pilot valve, but you're reporting actual flow. And for this last one, again, this is the catalog. I'm not saying this is a solution for everything, but if you have valves that are of high concern, that are bad actors, that are large, that are in severe HAP service, you might want to take a look at this because your report's going to look a lot better if you have a monitoring or a modulating pilot. Again, using that 50 to 60% number that we've gotten from history, we can tell that the difference to moving to a modulating pilot valve is about 40%. And in some release scenarios, you will only release about 10 to 20%, obviously depending on the scenario, right? So you're emitting just as needed and you're reporting actual flow. And by the way, we're at booth 4308.
4309.
It's right where the food is, which is a good thing.
It's a big scale. You'll see us there. We actually have all these technologies out there and we can actually demo them live. We are receiving it into a gateway. We have a computer, so we can literally demo each and every one of them to show how the data would be received back. So yeah, definitely stop by if you have any questions. Just want to see the demo in real life action. Pop a valve, creates a noise. Yeah, I'm happy to stop by, and we do have cowboy hats to give out too. So
Yeah.
Cowboy hat.
If you want a blue cowboy hat, we got you covered.
There you go.
All right, Mo.
All right. So all the solutions we've spoken up to now are more release event centered, right? So it's all about understanding when your release event occurred, when it started, when it stopped, and that's what the regulation asks for. Another issue or concern we have seen is with bellows, right? So this is more around asset health or valve health or bellows health, essentially. Bellows valves are used whenever you have any kind of back pressure. So if you have a common header and you have a bunch of valves going in there, more often than not, you probably have a bellows valve because there's some variable back pressure in that header system that the valve is going to see. Now, the reason it's there is because the green part in there, that's the bellows. If that's not present, any kind of back pressure offsets your set pressure by your spring. So you need to have a bellows. But when you have a bellows, it's a metallic component that compresses. And I think we have one out there too. And when it compresses, it needs to reference atmosphere, or else your spring chamber, which is your bonnet, becomes a pressurized chamber. So you need to have a bellows and you need to let your bonnet vent be open so it references atmosphere. Now the concern there is bellows over time fatigues because it's a metallic component over multiple cycles and it ends up rupturing. We have no visibility into the rupture. You could pull the valve out, do a pressure test and put it back in, and maybe all it's got is 2 cycles and it ruptures after 2 cycles. But you have no kind of visibility. The concern there is when your bellows does rupture, any kind of back pressure you have traces out the bonnet, and out the bonnet vent is freed of emissions. A couple concerns about this, right? So in Latin America, there was a chemical facility which had a similar bellows rupture and didn't have any kind of visibility. Lightning occurred, it caught fire, and the plant was down for a long period of time. Similar thing happened in the Northeast over here in the States. It was a kerosene service. Common valve header, one valve went off, increased the back pressure in the system. That back pressure caused another valve's bellows to rupture, and all that flare, what was going into the flare, was coming out the bonnet vent, and it was kerosene, so it caught a spark and it caught a fire as well. right? You've had situations where it's H2S gas. H2S gas is lethal. Luckily, you got caught because there was a workers monitor that went off saying that H2S gas, and they were able to figure out which valve it is. But it took them about 4 or 5 hours to shut it down, get people in mad, get everybody like in the attire you need to get out there and try to troubleshoot and find out which valve is actually causing this issue. Because H2S is a heavy gas, and something like if it settles down, you don't know which valve actually is leaking, right? So we've done a study of 30,000 service records based on different applications. We see that we expect about 2 to 6% of bellows in the field currently are failed or they are ruptured. Now, I don't know the severity of the rupture, but when a rupture occurs, there are multiple concerns. The first concern is it offsets your set pressure, right? So if your bellows ruptures, it's as good as you don't have a bellows. So your set pressure does not work the way it's supposed to. That means everything upstream of your valve is overpressure, because your valve won't open at the time it needs to open. So that's a big concern. Second concern is everything in your flare system or everything in your header system is now going out of your bonnet when this fugitive emissions, which could be either lethal or flammable. And then third is somehow if there's enough buildup and your valve actually does open, your actual process too will reference atmosphere through your bonnet vent and go out of your bonnet. Now, a couple of concerns there. In Houston, there was a facility where the service could not reference atmosphere because it would solidify. And they had a bellows rupture, and this did happen, and the valve literally just solidified, the whole spring chamber. That means your valve's not going to function no matter what. You have to pull it out. You have to turn on your whole service, things like that. So it is very concerning, right? And with the number of 2 to 6%, with quite a few bellows being out there too and not having any visibility yet is a concern. So what we've done is we've come up with a solution, which is essentially a twofold. All the technologies have existed independently for more than 50 years plus. We just combined them together and created a solution because we know there's a big pain point in the industry. The first one right here is an adapter, right? So it's a backup. You can think of it as a backup adapter to the bellows. When your bellows does fail, what this backup adapter does is it helps balance your valve against back pressure. So it negates the downward forces that would be put on the valve after the bellows is ruptured. So if your valve has to go up at 100 pounds, it will go up at 100 pounds because this helps keep your valve balanced against back pressure. The second thing is once your bellows does rupture, this is a limiting surface to your bonnet vent fugitive emissions, right? So it mitigates the amount that would be flowing out of your bonnet vent by more than 90%, depending on your orifice size. Because there are certain clearances within that piston that change based on the size. It's a complete machine surface. So it limits the fugitive emissions and balances your valve against back pressure. What the pressure transmitter does is it taps into the chamber between the backup piston and the bellows. So during normal operation, it's going to see 0 psi because your bellows is attacked. But as soon as the bellows does rupture, you get instant notification of when your bellows does rupture. So, and the transmitter again could be wired or wireless, so you have that flexibility. So now you know instantly when your bellows ruptures, you actually limit the amount of fugitive emissions coming out, and your valve is balanced against back pressure. The last added benefit is to simplify the solution, I guess to simplify the equation. We know P1, which is what the transmitter is telling us. P2 is atmosphere. We know the clearances in the piston, so we can kind of estimate the amount of fugitive emissions being pushed out, right? So once you see, if you know the kind of back pressure in your header system, you see the pressure on your transmitter, if it's the same, then you know okay, there's a significant rupture in your bellows because you're literally seeing the exact same pressure. And then you can even estimate the amount of fugitive emissions being pushed out there, right? So incorporating the one solution helps you kind of give you 4 different benefits of reducing the amount, calculating it, as well as maintaining your valve against back pressure and getting instant notification of when this bellows rupture does occur. So, you don't have people running out there trying to hear it for the whistling sound of which valve is actually bellows is the, venting right now and what's going on. You save it. You save yourself that kind of a hassle, right? So right now, LDAR usually refers to seam surfaces. So they check the flange to flange connections. But some states, some sites do have a requirement of monitoring the bonnet vent because that also is a source of fugitive emissions. So it is something that might be, we don't know yet, but potential based on how stringent the regulation is, potentially in the future there could be a mandate to bring everybody to go monitor that. But rather than sending someone out with a sniffer for all the hundreds of valves you have out there, this is a automated solution that can help you get that information, right? And once you get that time data back, you can actually do the root cause analysis of what caused the ballast to rupture. Like the one I spoke to you about Northeast, where one valve went off, increased the back pressure in the system that caused the ballast to rupture. It took them like close to 2 months to figure out what happened. Because first I had to like get all the pieces together, it was all burnt, figure out what caused what to happen, and then try to figure out what changed in the system, figure out the sizing issue, what went wrong, and then after 2 months, they were able to figure out what actually went wrong. So it just helps gives more insight.
Yep, just something to add there, just like Mo said, this is currently not a part of the law and regulation. Bellows, it's not required by the EPA to monitor those right now. But as the LDAR program start to get more stringent and they're starting to look into more of where leaks are coming from, we anticipate that this is something that will be a part of the regulation in the future. Because they're a huge source of problem. I mean, we talk to end users all the time, and one of the first things that come up when we say, hey, what's a pain point on your PRVs? Bellows, every time. We're changing them, we're blowing them out, you know, it's a huge problem.
That, like you mentioned, we're right there, right by the food. You know, stop by, see the valves, pop a valve, create some noise.
Get a cowboy
hat. Yeah, and we'll be happy to answer any questions that you have. So, yeah. That's all we got for y'all.
Thank you.
Thank you. Up. You get it.
Curious.
Yes.
When MaxCC and that RSR rule came out in 2019. So there was a lot of guidance documents, things that even PRVs that go to fuel gas systems and back to process that basically treat these as atmospheric valves now. Pilot operated and bellows valves would require monitoring on them. So have you guys seen any of that data for like looking at bellows vent, for example, or dome vent, things like that? Comparative for what you're seeing, like estimated emissions versus.
Versus,
No.